pleasure to have Chuck Doran again here. He's going to talk about Feynman Amplitudes from Calabi-Yau Fibrations.
Okay, thank you very much for the last minute invitation. Since I arranged the invitation for Andreas Malmendier in the first place and he had to pull out, I thought it was only appropriate that I substitute. Having said that, this is sort of a very informal presentation of the work already completed and some work in progress, I'll mention again, with Andrey Novoseltsev and Pierre Vanhove. Andrey is my former student and postdoc. Pierre is a physicist, a researcher in the area of Feynman Amplitudes. And as Pierre likes to say in many of his talks and in person, I'll summarize it here as a philosophy for mathematicians, the main questions about amplitudes in quantum field theory can be reformulated in terms of the Riemann-Hilbert problem, type problems for periods of families of hypersurfaces. Okay, so what does he mean by that? Well, he means that you want to do things like compute periods explicitly. You want to derive global monodromies. You want to construct a complete system of differential equations that you solve. And you want to understand the new class of special functions needed to express these inputs. So, more precisely, if gamma is a Feynman graph with n plus 1 edges, these are something known as propagators, so the internal edges to us, then the Feynman integral I sub gamma, and I won't give a formal definition, can be expressed as an integral over delta n plus 1 of omega gamma. So what's delta n plus 1 here? This is a positive simplex, so it's given by x1 through n plus 1 in R such that xi equals 0. Okay. These xi's are the so-called Schwinger proper times, but you can think of them as just formal variables of integration. Here they're real, but often one actually does computations with complex variables and specializes the integrals later on to sort of real integral. And this here, the omega gamma, is a meromorphic n-form depending on the other data in the Feynman graph of these physical parameters, so physical parameters. So these would be the external momenta and, again, the internal masses attached to the propagators. In particular, from this formulation, you're able to construct what are called the first and second semantic polynomials. But for people familiar with meromorphic forms, all you're really doing is you're specifying the numerator and denominator of this meromorphic form. Okay. In the simplest case, the denominator is all that matters. Now, there is an algebro geometric reformulation to, in this form, to block no primer that represents the same I gamma as a period. So, sorry about that.
Beautiful.
Yeah, it's a good ringtone.
It really is.
I think it's the wrong number too. Okay. So we expressed it as a period. So a period of what? Well, it's a period of mixed Hodge structure on the relative cohomology group Hn Pn minus our hypersurface, or graph hypersurface, and E minus X gamma. Okay, so B is called B because it's a blow up of our simplex. It's a blow up. This one. And this X gamma is called the graph hypersurface. Defined, naturally enough, by the poles of A gamma. Okay, so now, of course, if you vary the only variables to play with, which are these physical parameters, we get not just a mixed Hodge structure, but we actually get a variation of mixed Hodge structure, or a variation of Hodge structure. HS. And then the Feynman integral on gamma satisfies an inhomogeneous Picard-Fuchs equation. So the gas union connection doesn't annihilate it. There's something left over. That something left over is very important. So, as you might suspect, the source of the inhomogeneous term is extension data for mixed Hodge structures. And the dependence on parameters defines a normal function in the sense of Poincaré in Griffiths. Okay, so that's all I'm going to say in general about Feynman integrals. It's enough, hopefully, to convince you that as complicated as it may be in the physics literature, at some basic level, the story reduces to quantities that we as mathematicians can recognize and manipulate. In particular, periods of mixed Hodge structures, explicit solutions to Picard-Fuchs equations, inhomogeneous, okay? And connections to structures of interest in Hodge theory and geometry. It gets a little bit better than that because there's what I'm going to call a folk theorem. Which in various forms you can trace back to Francis Brown or Bourgeois, and they certainly highlighted it. In spirit, it probably goes back much, much further to some early computations in the field. But the folk theorem says this. It says that after inessential meaning easy contributions to the integral, simplifications, the periods that remain are associated with Calabi-Yau manifolds. So that's certainly something that here at CMSA cares about. So
Can I ask you some questions? Very naive ones.
Yeah.
Why is it that the algebraic translation looks like that? Why do you look at the? Is that the complement?
Yeah, this is common in sort of the Griffiths generalization of Poincare residue. So if you're trying to interpret periods on a hypersurface,
Okay.
the way you usually get at them is you say, oh, I'm going to consider differential forms which are meromorphic on the ambient space, whose singular locus is along the hypersurface. And then you have a Poincare residue, which relates
Right.
to. Yeah. So from the standpoint of formulating in terms of mixage structure, this is kind of the cleaner formulation. In practical terms, what ends up happening is that periods are going to be periods of X gamma.
I see.
X gamma will be the compact hypersurface carrying on.
I see. And your notation is relative cohomology of.
Yeah, it's relative cohomology of the complements of X gamma in Pn relative to, in effect, the complement of X gamma in the blow-up of that sentence. So, I mean, I'm not going to explain what this is. The actual connection here is to higher Chow cycles. And, you know, if you've played with those some, you know that these kind of formulations are all related. But what's important at this point is to recognize that these Feynman integrals, whatever they are going to be related to periods associated to the Hopf structures of hypersurfaces, which fits in very well with the lectures that Hussein Sadi's been giving. And in particular, that a critically important special case, and possibly the source of all non-triviality, in some sense, as contributions to these integrals, is the special case where you're working with periods of Calabi-Yau manifolds. Now, this is very much a folk theorem. This is not, I'm not at all claiming this is a general result. But in many, many, many examples, you see how to strip off easy, rational contributions. What's left after you stripped away all the classical stuff is some core period, and that core period is associated with Calabi-Yau. So for the examples we're going to talk about today, all there is the Calabi-Yau. Okay, so we'll make it easy on ourselves in that sense.
But I don't need to understand for your talk, why is it that it's translated like with that relative cohomology?
No, you don't have to know anything about that at all. All you have to know is that at the end of the day, we want to compute periods on compact Calabi-Yau manifolds. Yes.
Well, although we don't have to know that, but just to understand the context, how is this Feynman integral the same?
Yeah, these are the Feynman integrals in quantum field theory. These are the actual amplitudes that you want to compute. This is big D equal 2, if you care. But it's the same story. So, I mean, this is intensely relevant for the activity that's been proposed for next fall at CMSA. This is exactly the connection between amplitudes and Calabi-Yau geometry, I would say.
And the Feynman integral is over some infinite-dimensional thing, so this is a simplified version, but
I think somebody computed it and then they.
Yeah, I mean, what happens is
landed on this kind of.
I mean, this is why I'm saying that you won't, if you know the right places to look in the literature, you'll look at the papers by the physicists who've already communicated with mathematicians, as they've written things in terms of language that you like. If you go back to the original sources, it looks like everything is crazy, infinite dimensional, and nothing might converge. But you know, you have some reassuring theorems, right? You have a reassuring result of Francis Brown using techniques involving MG bar that tells us that
I think in particular he's also asking why is it that the base of your Feynman integral is finite.
Okay, this is not the Feynman path integral.
It's not the finite.
This is not the Feynman path integral. This is when you have a Lagrangian theory and you expand it in terms of Feynman graphs. Each Feynman graph corresponds to some contribution to the amplitude.
Yeah, though the path integral involves running your loops, but that shows up to day 2.
This is the usual classical formulation of quantum field theory in terms of Feynman graphs. Like if you draw a Feynman graph that means something, you write down an amplitude, you integrate over internal momenta that run in the internal edges.
Yeah.
That's what you're integrating over. The internal momenta, and then if you have gauge degrees of freedom, that kind of stuff. That's a priori already a finite dimensional integral.
That's right.
It's not necessarily renormalized, there might be infinities, you gotta worry about that kind of stuff, but it's already simplified to that extent. It's not starting from the Feynman path.
Right.
But then when you're summing over, that's an infinite sum. That's where you have to run the loop order.
I see.
So I'm going to illustrate perhaps the simplest non-trivial case of that today.
Then you expect to get the actual path.
Yeah, then after you finish summing up, that should be equal to Feynman
I
path.
see.
That's right.
Okay, very good. All right, so as I said, the focus today is a class of Feynman graphs whose graph hypersurfaces are Calabi-Yau manifolds. So this class is what's called the N loop. I think I've kept track of all my N's. Sometimes it's called the sun set. Sometimes it's called sunrise, depending upon your personality. Sometimes it's called banana. Graphs. Okay, so let me give the first example. I'll give a 2-loop. So we have 2 loops, so that means we have 3 internal edges. I'll label these externals and the masses. Doesn't matter. M1, M2, M3. Okay. Let's call this graph gamma n minus 2. Okay. So here n equals 3. There's 3 propagators with 3 associated mass parameters, M1, M2, and M3. L is equal to 2, where L is the number of loops. V is the number of vertices, which is also 2, and Euler's formula holds. V equals 1 plus m minus L, so we're good. Okay. What is the corresponding defining equation for the hypersurface here? Well, phi gamma 2 is x1, x2 plus x1, x3 plus x2, x3 m1 squared x1 plus m2 squared x2 plus m3 squared x3 minus p squared x1, x2, x3. So what this is a family of cubic curves. But it's better than that because we have these distinguished deformation parameters. So we can think of it as a family, this is important for later, of rational elliptic surfaces in many ways. For example, you can pick p squared as the base parameter for your family of elliptic curves and deform with the mass parameters. Or you can pick one of the mass parameters as your base parameter and deform with the remaining mass parameters in p squared. Fine. Be my guess. Do any of those ways. Let's see what it looks like if p squared is the base parameter. So letting p squared be the base parameter. So now thinking of this as a rational elliptic surface, we see that we have singular elliptic curve fibers, I2 type at p squared equals 0, I6 type at p squared equals infinity, and 4 I1 type fibers. Okay, well, their positions have to depend upon the masses, and they do it in a really neat way. P squared equal m1 plus m2 plus m3, m1 minus m2 minus m3, minus m1 plus m2 minus m3, and minus m1 minus m2 plus m3.
Is there a way to read off the equation of the hypersurface by just looking at the graph?
Yeah, there is, but I'm not looking at that. So the graph, together with the momenta and mass parameters, is enough to determine the polynomial, but still better than that, so the topology of the graph is not in terms of the form of the polynomial. Right. So for instance, if you take a case where all the mass parameters are equal, these m squared is wiped out. Okay? But you still see the shape of the polynomial. And this is the dictionary. I mean, the overall shape of the polynomial dictates the topology of the graph. The topology of the graph dictates the overall shape of the polynomial. Throwing in the physically meaningful parameters, the p squareds and the masses, or the p's and the masses, momenta and masses gives you the form with actual deformation coefficients. Now, if you want to say, oh, this seems incredibly special, they are, okay? These are very, very special examples, but they're illustrating some lessons that I think, due to the Folk theorem, are key to understanding. Okay, so we're looking at this two-loop sunset to begin with, two-loop curves. Now, with arbitrary mass parameters and letting p squared be the base parameter, we get a family of elliptic surfaces dependent upon M1, M2, and M3 with an I2 fiber, an I6 fiber, and 4 I1s. Okay? But, and this is important, in the special case where all masses are equal, this becomes I6, I2 as before, but now an I3 and an I1. Okay, so this is your I1 and these cluster together to give you I3. Switch that around, make it easier to read. Okay? Now, this is in fact, this is one of the elliptic modular surfaces. So I'll also call it semi-stable elliptic modular surfaces. Studied, for example, by Beauville. And corresponding to, well, it has to correspond to a subgroup of SL2Z or PSL2Z, so this one corresponds to gamma mod of 6. Okay. Now, in its guise as giving rise to a two-loop final integral, it was studied by Bloch and Vanhove. And they showed that the corresponding integral, well, okay, first I'm going to say the highbrow interpretation for what they showed, and then the practical consequence. So the highbrow interpretation is that it's what's called a regulator period. Contain Milnor symbol in case of 2, that's algebraic K2 of the elliptic curve. Okay, so that's what I call the highbrow intrinsic interpretation of what's going on. And in practical terms, they expressed it in terms of elliptic dilogarithms. And of course, this case is so foundational that many of the observations here predate this particular approach to the problem, but using this sort of motivic interpretation, you can rederive all the observations. Okay, so what happens if you go from 2-loop to 3-loop? So, 3 loops. So 3 loops, we're going to get this picture.
In the physical theory, P is what?
P is momentum.
But then you can think of it as a parameter?
Yeah.
No, but somehow for a... No, of course you can think of it as a parameter. No problem.
The novelty is that we're thinking of these things as actual complex parameters. And the ex post facto, you worry about specialization.
Yeah.
You know, cuts and whatnot. Real simple. Okay, so here's gamma 3. So we have our P's and then our M's. We're backwards. M1, M2, 4. Okay, so now we have N equal 4 propagators, L equal 3 loops, and B equal 2 vertices. And phi gamma 3 takes the form x1, x2, x3, plus x1, x3, x4, plus x2, x3, x4, plus x1, x2, x4, times m1 squared x1, plus m2 squared x2, plus m3 squared x3, plus m4 squared x4, minus p squared x1, x2, x3, x4. Okay, so we have a family of quartic K3s.
Why do you call it 3 loops? How do you count the loops?
1, 2, 3.
But
Doesn't count.
doesn't count.
Oh, it's 3 loops.
No, but why can't you have a bigger loop?
You could introduce that notion, but it's supposed to be the internal loops. In this case, you introduce that notion.
Maybe one of them is the configuration of P, what is like P greater.
Yeah, you imagine P going off.
Yeah, there is one,
Right.
I don't know.
No, you imagine the P kind of going off both ways or something.
No, I know, but at least internal loops could be M1, M4.
But you see, I never use this for anything, right? This is just indexing, right? You can declare your definition of loop to be one higher if you prefer. It doesn't make any difference from your ball. This definition of loop makes the order formula work where everything down. So again, let's do as before, and even though we won't want to do this eventually, let's specialize to the simplest case where all the masses are equal. Okay, so the last time when all the masses were equal, we got this modular family of elliptic curves, I6, I3, I2, I1, okay? And now here, in the special case, where all masses are equal, this becomes a family of, well, okay, I've seen you talk here before, it's going to be lattice-polarized K3s. The question is, what is the lattice polarization? So it's a family of a familiar one. It's M3 polarized K3 surfaces. Okay, we're here M3 is H plus E8 minus 1 plus E8 minus 1 plus 6. Okay, if you like, the mirror family to sextic K3s. Now, in particular, the generic such member is carbon 19, and there will be jumps densely to carbon 20. Okay? So this family of M3 polarized K3 surfaces studied in Helena Barrel's thesis. So this is her Cambridge University thesis from '94. Now, before, in this case, with all masses equal, we saw the total space was a rational elliptic surface. Now the total space is a Vanhove threefold. And again, in follow-up to the earlier work, Bloch, Kerr, and Vanhove. So specifically in equal masses case, show that I gamma 3, well, this one, regulator period interpretation, basically gave you a normal function interpretation. Now it's a higher normal function. So normal function involving higher child groups. Higher normal function coming from a family of elements of, okay, algebraic K3 of a K3 surface. Which is a joke that Matt and I made in one of our old papers, and it turned out to be exactly the right thing here. And is expressed explicitly in terms of now elliptic trilogarithms. Dialogue and trilogue. Okay, so after that little warm-up, let's start with a couple of questions. We'll try to take these as motivating questions for the follows. Questions. First, obviously, what about the end loop case? In particular, as maybe you're getting a little suspicion of, can we reduce the end loop to the n minus 1 loop and proceed iteratively? Okay. Second question, what happens when we move away from this equal mass situation? So they worked with equal masses because it was the easiest thing to do. Equal masses meant they really only had two parameters to worry about, the mass parameter and the p squared. Okay? So what happens when you put in the more general dependence on mass parameters? So we'll address both of those. Let's start with the first observation. So I would say a moral lesson from studying special families of highly symmetric or very special hypersurfaces projective space is that quite often something can be gained by reformulating them as more generic, less special hypersurfaces in toric varieties. Okay? Sometimes they can be like the generic anticanonical hypersurface in a Gorenstein toric fauna variety, in which case all the machinery of Batarev and Borisov, or Batarev in this case, applies. That might be asking for too much, okay? But at least we should try to learn something from the toric picture. So the first observation is to reformulate the n-loop sunset family of Vanhove one-folds using toric geometry. Okay. So the first step of that is just to pass to the polytope. And then observe structure of the coefficient weightings. So how the monomial coefficients depend upon the physical matters of mass. So on the coefficient. Weightings. Okay. So let's start with n equal 2. So for n equal 2, we get a hexagon. In fact, after suitable blowing up, the del-pezzo surface that you get by blowing up P2 at 3 points is the total space. Okay. So you get a hexagon. Now, a priori, the hexagon is not centered at the origin, so we're going to center at the origin by subtracting 1. Okay, and then you get a reflexive polygon. This technique works in general. So you're always going to be able to take one of these families and reinterpret it as sitting naturally in a toric variety, okay, a toric variety that's not projective space any longer. How does this look specifically, though, for n equal 2? Okay, well, so there's the origin. Then you have
Are we allowed to have zero mass? Well,
no, that's a very good point, because if you go to zero mass, then you reduce to the previous case. So no. Now, in this theory, the way we set it up, zero mass actually makes sense in a degenerate limit. And then you're going to get a relationship between mixed Hodge structures and Hodge structures. And so there is a sensible way of doing that, but generally speaking, it's a bad idea because it's going to make all your formulas for periods go haywire. All right, so now I have some colors here, so let me use them. So first of all, I'm going to use purple to mark the point that's weighted by p squared. Okay, it's also weighted by a lot of other stuff, and in fact, the stuff it's weighted by can be organized in terms of cones down to the origin, cones over faces, or generally facets. Okay, so I get this one, which corresponds to m1 squared. I already said that p squared is the origin. Colors blue by blue. So m2 squared is here. And then here's yellow. Okay, so what's going on here is that we have a reflexive polygon, happens to be this hexagon, okay? And then if you actually look at the weighting of the coefficients, you see that they organize themselves very naturally. It's a subdivision of the vertex set into a union of facets at each cone over the origin, and then the cone, which is the trivial cone, the origin itself. Okay? So this is a combinatorial, this is the combinatorial structure that's being overlaid on the reflexive polygon to give you the exact data you need to specify this family. Yes?
Did you rewrite the equation?
I can do it. I can't promise that there isn't a flip or something else that you take one to the other, but you can write it down. You want this one.
So we can compare with this.
So you want phi down 2. So x1, x2, plus x1, x3, plus x2, x3, and 1 squared x1. 2, 3, minus p squared minus 3. Up to some kind of GL2 transformation, probably a flipping sign, and of course the shift I told you about. The Newton polytope will give this hexagon. Okay, so 3, 4, 5, 6, good. All right, so what does this mean? So, right, so the point is somehow that what our translation is we start with this expression in projective space, we do the obvious thing, we construct a polytope, which is a Newton polytope. We observe that by shifting to the origin, we get a reflexive polytope, but we're not dealing with a generic anticanonical hypersurface in this guy. We actually have conditions, but the conditions are combinatorially natural. They're literally this kind of marking of cones, okay? With the origin being a distinguished cone as well. So, what are the implications for n equal 3? And remember that as long as we have unequal mass parameters, in some sense we're learning something new, even in the case of n equal 3 or n equal 2 for that matter. Well, we'll get it. So n equal 3, okay? Well, what kind of polytope do we get? Here we got the hexagon, okay? That's got the maximum number of points or the maximum number of edges of any reflexive polygon. Now we get the unique 3D polytope, so reflexive polytope with the maximal number of faces. Okay, it's actually got 14 faces and 12 vertices. Okay, if you like, it's number 1529 in SAGE. Andreas Novoseltsev was my student who actually ported the palette into SAGE. So the numbering scheme starts with 0. That might be our fault. In any case, it's 1529 in the SAGE. Okay. Now again, the weighted cones consist of, okay, well, it's the origin, p squared, and now it's 4 3D cones on qi, I equal 1, 4, over, I'm going to say, every other triangular face. So the way this polytope looks is that you have, as I said, 12 vertices, and the actual facets, the faces, are all triangles and quad faces. So you have a quad face with 4 triangles on it. Each triangle is obviously adjacent to the quad faces. So, but touching another triangle at a vertex. So what ends up happening is that the triangles there's a bipartition of the triangles. You have a triangle, and you can ignore its nearest neighbors, but take the nearest neighbors of those. Okay? And those are the 4 we're talking about. It doesn't matter which triangle you start with, because they're all equivalent under symmetries, but it's going to be every other triangle. Okay, triangle, it's adjacent at vertices to 3 other triangles, skip those, take the 3 triangles those are adjacent to, and skip the last one.
If I take 2D slices of this one, do I get that?
Yeah,
Each
so
direction.
this is part of the story. Okay, part of the story. There are actually quad slices and hexagon slices here. And so yeah, that's actually part of the story. All right. Now, here's things get fun. So the Minkowski sum of the QI, running over all 4 of them, and then up to over some overall flip. Okay, so gives the reflexive polytope whose points correspond to the quartic monomials in P3. So that's a direct connection between this modified polytope we're dealing with and its combinatorial structure. Right? You're saying take the Minkowski sum of these and projective space. Okay. Also, the duality between reflexive polytopes and the Minkowski sum convex hull, which is certainly familiar to anyone who's played with the Borisov theory for complete intersections, but here we're only dealing with hypersurfaces, applies with the dual cones pi, I equal 1 to 4, being 1D cones, one polar. Okay. So to complete the picture, its compatibility with this sort of combinatorial duality, P1 Minkowski sum up to P4 reproduces the polar polytope to this 1529. The convex hull of P1 to P4 reproduces.
Why is it that we are taking like Minkowski sum? Just
Sorry,
take the union.
Sorry,
What is the
what is the Minkowski sum?
Like the vectorial sums.
Right. So the reason for it has to do with the fact that in polar duality, convex hulls are, in a sense, dual Minkowski sums. That's the principle at work. It's a combinatorial duality that's exploited in the context of complete intersection polynomials and toric varieties. But here, we're exploiting it in a more basic combinatorial level. So let me finish and see why like this. Okay, but then Q1 and Q4 convex hull gives the polytope 1529, and Q1 plus Q4 gives the polytope. Okay. So there's a sense, very strong sense now, that we really are not very far in this family from the toric polytope, if you like, or the toric variety Pn itself. Okay? It's Pn with a little bit of decoration. Okay, that's what's going on. All right, so this generalizes to the analytic case. Okay, and is the key to understanding via, again, as we're talking about, via, I'm going to say, reflexive slices. Okay, it's actually reflexive slices / projections, depending on which polytope side you're on, and iterated, torically induced vibration structure. On the end loop sunset. So I won't go into detail, but in effect, what's happening on one of the sides, you're getting a slicing by the previous polytope from the previous step. On the other side, you have a projection to the polar. In the case of a hexagon, of course, it's its own polar. Shouldn't be confusions. What it does, this combinatorial structure does, is it makes it clear then that from the standpoint of constructing the families, there's a very, very simple combinatorial recipe. And because of this torically induced vibration, you see that it's compatible with the presentation in the ambient space. Okay, now what's the implication?
So is the idea of taking the kind of Minkowski sum or the convex hull that somehow, in some sense, you're producing a generic family of these polytopes, right? I mean,
Generic subject to these combinatorial conditions. Yeah.
in some sense, you're filling the gaps, and that is what allows you now to guarantee that if you take a slice, you will get the one in the previous step.
There may be something to that philosophy. I'm thinking of something more prosaic. When one first works with these examples, you realize that there are these torically induced vibrations.
Mm-hmm.
You want to systematically generalize them. That's easy. You can do that. But you also want to understand why they persist. And at some very basic level, if we were talking about just a generic anticanonical hypersurface on a toric variety, the whole story would have to do with the toric slicing. This happens all the time in applications in physics, where you take advantage of this kind of slicing and projection, but you're still working with the generic anticanonical representative. Here, you're non-generic. So whatever additional combinatorial structure you need to specify the family also has to be compatible with the slicing and projection story. And that's what's being observed by this extra structure. Okay, so it's a way of abstracting what's going on in practical terms. You can certainly write it out all in terms of equations in projective space, but this makes it a lot more clear. The implication for the Feynman integral is that I gamma n plus 1, p squared, mi squared, I equal 1, plus 1, can now be written as It's an integral 0 to infinity, and there are many ways to write this. I'm just picking one of them. P squared, n1 squared, n minus 1 squared, square root, n squared, I'll say an auxiliary variable s, which I'll integrate out, plus m plus 1 squared, 1 plus s, over s, over s. Now, this is the non-trivial bit, okay? There's two non-trivial things about it. One is, of course, it's got some expression in terms of mass parameters from the previous case, mixing it up with the new parameter n plus 1. But critically, it mixes with an old mass parameter, okay? So this is going to have multiple implications for us, and one of them is it explains why this formula was missed before. So when people studied the equal mass case, they missed this. Why did they miss it? Because it was impossible to distinguish the new mass parameters from the old mass parameters. The simplifying assumption obscured the method of expression. Okay, we'll see this in geometric terms in a minute. Okay, so what's the geometric phenomenon at work? Well, it's something that's familiar from, for instance, my lectures in May. So the geometric phenomenon and by this I mean the intrinsic geometric phenomenon, okay, that's taking advantage of all the structure present and strips away the inessential, is that the n-loop sunset gives rise to a family of Calabi-Yau n-1 folds, each of which is a double cover. This is square root here. Okay? It's a double cover. Of rational total space of the family of n-1 loop sunset Calabi-Yau times 2 folds. Okay. So literally the total space of our family of elliptic curves, which is a rational surface, is suitably double covered, inducing, by double cover of the rational surface, inducing an elliptic fibered K3 surface structure on a family of K3s. Okay? And because you have 2 points of branching over the base, if you fix one of them, the other one becomes your deformation parameter for the K3 family, and lo and behold, that's the structure. Okay? So let's just see how this works in concrete terms. So for generic masses,
Something is still which I don't understand is
yeah,
when you start from this Feynman diagram, right?
yeah.
You have that. I mean, you get these QIs. Get the QIs.
I get the QIs.
Even torically, you can just look at the union of the two, and those are precisely the ones that should give you that diagram.
Yeah, the QIs correspond to the MIs.
But now, exactly. Now you're taking the convex hull. You're diverging away from your original diagram.
That's the point. Okay, so the convex hull here
Yeah.
is by construction just the polytope we started with. The Q's are cones on this polytope, cones over the faces of the polytope, the facets of the polytope over the origin. They consist of, each one of them consists of 3 of the 12 vertices of this thing.
Okay, I
That's
understand
it.
now.
Okay. So I mean, again, this is an almost tautological.
And this is the polytope you gave over there. Okay.
That's the polytope I gave over there. That's
So
right.
it's no,
So
you're
what's-
not diverging.
No. So what's interesting about this, what's fascinating about this from the standpoint of, if you like, information theory
These
associated
are
with the family,
cones over those vertices.
yeah, is that
With
this
friends.
marking, it creates an intimate relationship between the Newton polytope that you get and the original polytope repeat.
Yeah, I didn't know what
It's
QI
beautiful,
was.
it's beautiful
Okay.
response. And it generalizes all dimensions, and then you can see the vibration structure of
Okay.
toric being
Okay.
used.
All right.
Okay, so now let's look intrinsically. Let's try to see what evidence for this that I just said here, this claim. So for generic masses, for the three-loop sunset, K3 surfaces. Okay, these have, this is the torically induced elliptic vibration. We have an elliptic vibration induced torically with fibers of types 2I6, 2I2, and 8I1. Now, this is exactly twice the fibers we had for the generic mass case for n equal 2. Okay, the 2 loop. So yes, indeed, and this is literally what's happening. You can even look at the defining equation in Weierstrass form, and you can observe that the positions of these two are given by a quadratic term whose origin comes from the rational elliptic surface and double cover. Likewise here, likewise these parallel into 4 terms. Okay? So it's exactly that story. It is double cover. Of the generic masses 2-loop sunset family. Okay, good. Now, if you consider instead an equal mass case, however, what happens? Well, in the equal mass case, so all equal masses case, the corresponding elliptic vibration is 2I6, I4, 2I2, and 4I1. Okay. So, which cannot rise as double cover of the Bovial. We had an I3. No way. Okay. So it does, however, arise as double cover of 2 independent mass 2 sunset rational surfaces with now I6, 2I2, 2I1. Okay, so one of these I2s gets doubled, the 2 I2s, the other I2 has branching order 2 giving you an I4, the I6 gets doubled, and the 2 I1s get doubled. The remaining branch point is the new modulus. So it's completely natural intrinsics. All right, that's enough on the first question. What about the second question? So the second question was, what about this mass parameter dependence? We've seen from the answer to the first question that the mass parameter dependence is really important. You just can't settle the masses equal and expect to understand what's really going on. So for the second question, and I have how much time? 5 minutes. So for the second question, we'll focus on the 3-loop sunset, surfaces. Okay, and it's useful to sort of map out the mass parameter dependencies. Even with this beautiful picture with the elliptic vibrations and K3 vibrations and the Calabi-Yau threefold vibrations, it's still useful to use toric information. Okay, and the reason for that is toric geometry gives you something concrete you can actually hold on to. In particular, toric geometry, by intersecting toric divisors with the hypersurface, can give you, in the n equal 3, for the 3-loop case, actual rational curves on the K3. Okay? So toric geometry, toric methods, intersecting with toric divisors dealing with splittings, gives you 20 rational curves. You then have to confirm that in fact your 20 rational curves give you the full narrow and severity lattice. They generate that, okay? Span that. And then you show that narrow and severity actually has rank 16. You have an explicit relation. Okay? So you have the narrow and severity lattice. This is important because the reinterpretation of these in terms of elliptic fibrations results in Mordell-Weil groups that have positive rank. And traditionally, if I tell you I have an elliptic surface, here are my bad fibers, okay, maybe I'll even tell you the torsion of Mordell-Weil, and I tell you it's a K3, you're going to be able to tell me the rank of Mordell-Weil, and you have no clue as to how to go about finding the actual generators for Mordell-Weil, the infinite order generators. So having them from toric geometry is incredibly powerful, really, really useful. Okay. What ends up happening is that when the four independent masses go to 3 independent masses, our rank 16 goes to rank 17. And it goes from 3 independent masses to 2 independent masses. Rank 17 goes to rank 18. And we go to all equal masses. And we already saw this unique example at the lattice-polarized, and its rank is 19. In fact, there's more than one way with respect to this elliptic fibration slice choice to make the masses coincide, right? And that results in different expressions for these lattices. All right. Yes, okay, so the last comment in the remaining 2 minutes has to do with computation of Picard-Fuchs equations. So as you saw from the beginning, there's this connection to the sort of Riemann-Hilbert style questions, and it's really important to know how to compute Picard-Fuchs, okay? Now, there are various brute force approaches that involve working with series solutions and trying to sort of guess a differential operator they close on by going high and high enough order for the rational function coefficients. This is surprisingly effective in many cases, but it has lots of problems, right? You don't know how far to go. You have a lot of extra work to do to understand the meaning behind these coefficients that you find, okay? On the other hand, with this construction, okay, one of the morals of this construction is that if you switch the tension to m1 squared instead of p squared as the independent parameter for Picard-Fuchs ODE, it's more natural. Okay?
But Picard-Fuchs, you need to run over all possible.
That would be the Picard-Fuchs system, okay? Sufficient for the application to physics in many cases is to compute the parameter-dependent Picard-Fuchs ODE, okay?
The parameter is the one that gives you the type of the fiber depth.
Yeah, the parameters are the only parameters present, which are the p squared and the mi squared. So you have to pick one of them to be the base, right? Period and ODE. And the rest of them are deformation parameters. So in the language of my thesis, it would be what's called a geometric isomonodromic deformation. So it's a family of slices of, in this case, Calabi-Yau hypersurfaces, where you're computing Picard-Fuchs on each slice and you're deforming it.
That's fine. That's fine.
So you'll have lots of apparent similarities. But again, that's the price you pay for working with an ODE instead of a PDE system. And although we are well suited for using GKZ methods for the generic number, another approach would be to use the marked cone picture to try to soup up the GKZ method to actually get as concrete information about the subfamilies. But again, you have to go pretty deep. So the n=3 case, the generic anti-canonical has Picard rank 11. And we have to work with Picard rank 16 for our subfamily. So there's a big cost to pay there. Okay, But if you do this trick, then we can use a modified algorithm of unknown Besser and Malmendier developed for computing the uniformizing differential equations for Shimura curves to compute the Picard-Fuchs. So you have kind of an intrinsic tool to use that uses this intrinsic internal geometry to compute the Picard-Fuchs system rather than relying upon other methods, computational methods, often numerical methods. So work in progress involves extending the motivic interpretation that, as we talked about earlier, applied to the equal mass case, to the unequal mass cases and to higher dimensions. And then also, this is kind of neat, clarifying the role of local mirror symmetry. So in the all equal masses n equal 3 case, 3-loop case with K3s, a really interesting connection to local mirror symmetry was observed as an application of my old work with Matt Kerr in one of the papers by Blocker and Vanhove. There's not really a robust explanation yet for why it deserves to be there, why local mirror symmetry should play this kind of role. And a really interesting question is to see how that extends to higher dimensions. As I said, with these other mass parameters, a potentially very deep question would be to connect that with the version of mirror symmetry, which is not local mirror symmetry, that applies to fibered or iteratively fibered Calabi-Yaus, and that's the DHT conjecture that I also talked about before. There, the mirror family is going to be a Turing generation, and if you iteratively fiber, it's going to be a deeper and deeper generation. And so that begs an A-model interpretation in terms of variation in these structures, and that's all to be dealt with. Thank you.
Any questions?
Maybe you have to mention that these hypersurfaces are very, very singular. At least last time when I was talking with Pierre, except the first one, the rest, apparently they are.
No, so what happens?
And,
so this is the inessential simplification I mentioned earlier. So what typically happens is that the hypersurfaces are singular, but quite often what happens is that the locus that you care about for the integral turns out to be a period along the branch locus. And then that's not going to be singular eventually. So you end up stripping away all sorts of inessential easy bits. The way you would teach a student to simplify a complicated integral, and at the end of the day, the core that's left, you can't solve by traditional means, turns out to be the period of a Calabi-Yau. That's a folk theorem. That's not a hard theorem, hard and fast theorem. But that's also a motivation for studying this case where you have none of those inessentials. Okay. Now it's misleading, right? Because a lot of people say, oh, if I want a smooth hypersurface to be Calabi-Yau, according to these rules, this is the only family. Well, that's true if you want the entire integral to be nothing but a period of a single smooth hypersurface projective space. Yes. But if you buy into the bigger picture, which is that set up a complicated graph, complicated system, and strip away the inessentials, that what remains is going to be contributions from core Calabi-Yau pieces, then you begin to see what I think is really going on.
And you're saying that your system is 2 degrees of freedom, including mass and momentum parameters, but you're not really allowing masses to degenerate.
Well, you are, because you separately do that analysis, but in this geometric picture, we can let the masses degenerate. There's nothing wrong with that, because we know what happens, right? The positions of singular fibers are related to these things. If mass goes to 0, then something's going to go to 0 or go to infinity. Or
so you're allowing mass to flow.
In the geometric picture, yes. I don't want to claim that the integrals are well defined, because typically they're not. I mean, this is the same sense in which a variation of Hodge structure in a limit might, or a variation of Hodge structure might in a limit be forced to be interpreted on the boundary of, say, moduli space or multiparameter family That's a variation of mixed Hodge structure.
Okay.
And then you have to find the pure self-Hodge structure, and then that's the part that survives the limit. So the whole game here is part of a much broader picture which I think was laid out originally by Spencer Bloch, or maybe Bloch and anyway, I'm not sure. But the general picture is one of limiting mixed Hodge structures are a great source for special functions and special values of special functions. That's the basic principle. And since everything coming from the physicist computations of these amplitudes ultimately suggested this kind of origin, if you're a geometer like me, you want to believe that there's a simple geometrical explanation for all these, a geometrical source mediated by Hodge theory, and that's what we're doing.
Any other questions for Chuck?
Yeah, is the sunset graph physically important, or is it just a good
Yeah,
source
so
for
Pierre tells me that it is physically important, and that the fact that we run the loops off to infinity matters for some application in physics. I'm not clear on the details of that. But again, the application we're talking about is not an application in string theory. So one of the novelties here is that the compactification spaces for string theory are playing an interesting role, and then one of the observations up till now has been mirror symmetry, now possibly, honest to goodness, mirror symmetry for iteratively fibered compact Calabi-Yaus is going to play a role in such computations.
Any other questions? If not, let's catch up.